Hello everyone. This lecture is about logic gates and logic circuits. As we know that this topic is a common topic in O and AS level, and then further afterwards in A2 it gets extended and becomes more complex in the form of Boolean algebra and other bit manipulation and all. So this one is especially with the reference to O level and AS level. So about logic circuits, whatever the gadget, the device that has some sort of logic in it means that if we can control it and we can set parameters of it and then it works according to our settings and all, there these logic circuits are being used. So let us start. As you can see over here, there are key terms that we need to first discuss. These key terms are logic gates. So logic gates in electronic circuits, which rely on and off logic. These are logic gates. The most common ones are NOT, AND, OR, NAND, and exclusive OR. We have these six and NOT in our syllabus. Second one is logic circuit. Over here, logic circuits. Logic circuits. So logic circuits here. So logic circuits are formed from a combination of logic gates and designed to carry out a particular task. The output from the logic circuit will always be either a 0 or 1. Then we have got truth tables. So it is a method of checking the output from a logic circuit. They use all the possible binary inputs combinations depending on the number of inputs. For example, 2 inputs have 4 possible binary combination and 3 has 8. By saying 8, I mean from 0 to 7, and by saying 4, I mean from 0 to 3. And then ultimately we have a Boolean algebra, though the topic is in A2, but the term is there. It is a form of algebra linked to logic circuits and based on true and false outputs. So what are the steps that we need to cover the topic? First of all, it is knowing gates and drawing circuits. It is absolutely necessary that we should remember all these 6 gates along with their working, their background, and their behavior in a circuit, and then how we put these gates together to form the circuit. Finding mathematical equations and Boolean expressions out of logic circuits. So as in binary number system, we can represent a number in binary as well as in denary and then in hexa. Similarly, a logic circuit can be shown using graphical circuit, a mathematical way, an equation, and in logical way, a Boolean expression. So we will be learning all these 3 forms. And then we have to learn how to make circuits out of the equations and expressions. So first we will turn everything to these logical statements and graphical representation of the circuits and vice versa. If we would have to actually learn how to convert between all. Then we will be understanding real world scenarios. Real world scenarios means that how if we have any real world situation, how we will be able to convert that situation into the form of circuit and then bring that circuit to our use. And then we have got truth tables. We will be learning truth tables. Truth tables are basically a method of checking the output from the logic circuit. And then we have got building blocks, and afterwards we will be discussing past paper questions. Building blocks I'll discuss when we will start. So first of all, let us start with symbols themselves. First of all, we call these symbols military symbols. Why do we call it MIL symbols or military symbols? MIL is the short form. Back in 50s and 60s, American military actually standardized these shapes of the logic circuits, and afterwards American National Standards Institutes and Institute of Electronic and Electric Engineers, IEEE, NC and IEEE formalized it. So before the existence of IEEE, IEEE is actually the organization, the private organization, non-profit organization of all the electric and electronic engineers to form standards. So does NCA and SI. Before that, before these organizations were made, it was just the militaries, especially the US military, who used to do all these researches and standardized the engineering. So actually Pakistan military, US military first formalized these shapes, and with that reference to the basis of it from the origination, they informally call it military symbols. And then every shape has got a logic attached to it. And then, as I said, that this shape can be expressed in logical way and then in mathematical way. A mathematical operator is also attached to it. And then there is a way to form mathematical equations and then Boolean expressions. So the first shape, this one, is called OR. OR is not the name of the shape, this is the logic of the shape. And then we have got exclusive OR. So what's the difference between OR and exclusive OR? So let's suppose that we have got these two pens. One is silver, the other one is black. And you are given option to choose any of them or both of them. So if it is OR logic with OR gate, then you can choose either of them or both of them. Whereas if it is exclusive OR, in that case, you can choose either of them, but not both of them. So exclusive OR is different from OR in a way that in OR you can choose any of the options or all of the options, but exclusive OR protects you to choose everything. It only lets you choose either of them or few of the options, but not all. So the mathematical operator related to OR is plus sign. It does not actually represent, it's just the monumental way of showing it. It does not add it. If it would have added it, then we would have gone out of the binary system, because logic circuits always act on binary systems, so it always 0 or 1. Then we have got this equation. So if you could see that there are two inputs, A and B, and there is one output X. So we can represent this graphical representation this way. X is equal to A plus B, and we know that this plus is actually showing OR. Or in Boolean expression, in the logical form, it is X is equal to 1 if A is equal to 1 or B is equal to 1, or simply X is equal to 1 if A or B. It means you can choose either if it is one input true or the other one or both. It is that way. So if we go with exclusive OR, the symbol is encircled plus. We call it XOR EOR or EXOR, but the most famous one and most probably that we will be using would be only XOR, so exclusive OR. So the formation of exclusive OR is either of these four, but the most famous one is this: X is equal to A exclusive OR B. It can also be represented this way: X is equal to A naught B or A B naught, or X is equal to A plus B and A naught plus B naught, or X is equal to A naught B plus AB naught plus AA naught plus BB naught. You don't have to, don't worry, you don't have to learn all these. All you have to remember is A exclusive for B. Then why I have used these three and shown these three? Because of the reason that many of the teachers or the books depict all these forms. So I wanted to tell you that all you have to use is use the first one. And similarly, in logical way, it is X is equal to 1 if A exclusive for B. Simple. Remember, we don't have to actually use any complicated form for exclusive for. Then we have got AND. AND is very simple one. AND gives you option to choose both of them. It does not allow you to choose either of them. So let's say if you have got these two pens, one silver, one black, the AND gate always makes sure that if you choose both of them, and you are not allowed to choose either of them. So it is different in a way from OR gate or exclusive OR gate, where it's a different scenario. So AND gate means that whenever all the options are chosen or all inputs are true, only then the output will be true. So as the relation goes, mathematical operator is multiplication. The equation could be X is equal to A dot B, X is equal to AB, or X is equal to A multiply B. It's your choice, doesn't make any difference, it's up to you. And then we have Boolean expression, X is equal to 1 if A and B, or maybe sometimes if X is equal to 1 if A is equal to 1 and B is equal to 1. Out of these 6 gates, just NOT gate has got one input, and rest of the gates may have more than one input. So NOT gate is also called inverter, and sometimes, most of the times, it is called NOT gate. So we can show it by having an apostrophe as prime or a bar on top of it. So I will be using both X is equal to A naught or X is equal to A naught. I would not be calling it prime or bar. I would rather be calling it always not by the reference of the gate. So X is equal to not A is actually the form. Remember, to show false, we don't write in Boolean expression 0. Rather, we call it not 1. Because it is a binary system, this is binary logic circuitry, so it is always either a 0 or 1. So if it is not 0, it is 1. If it is not 1, it is 0. But nothing else. So you may write it the way X is equal to 1 if A is equal to not 1. Or X is equal to 0 if A is equal to not 1. So the best form is X is equal to 1 if A is equal to not 1. Now, then we have got last two gates called not or simply NOR, or not AND or simply NAND. These gates are the combination of OR in case of NOR. I'm talking about NOR, OR and AND. When we combine these two, it becomes not OR. What does it mean? Whatever the output of OR, it will be inverted. It will be converted to the other form. Means if the output of OR is 0, it will become 1. If the output of OR is 1, then it will become 0. So you may write it like this: A plus B whole not, or A plus B whole bar. So this is not or. So how do we write it in Boolean form? X is equal to 1 if not A or B. All right, so you need to remember that if the not is over the whole expression in Boolean, or the whole equation in Boolean form, in Boolean expression, we have to put it first and then we will use brackets. So as you can see over here, X is equal to 1 if not A or B inside brackets. So this not applies over the whole output coming out of the brackets. And then we have got not AND or NAND gate. What does it mean? It means that whatever the output of AND gate, it will be inverted. So if the output of AND gate is 1, it will become 0, and if the output of AND gate is 0, it will become 1. So this is said to be NAND gate. As you can see over here, X is equal to AB whole not. All right, as I said that I won't be using the word prime or bar or whatever, I will rather be calling it not. So X is equal to 1 if not A and B. That is very simple. Now the most important thing that you need to remember, that these NOR and NAND gates are said to be universal gates. Why do we call it universal gates? For the reason that a universal, let's first discuss what is a universal gate. A universal gate is actually the gate that can implement any Boolean function without having a need of another gate, another type of gate rather, I would say. What does it mean? It means that if you have got a logic circuit which is comprised of so many different kinds of logic gates, if you take just one universal gate, either NOR or NAND, you can build the same circuit with just one gate. So even so much so that you can use multiple NOR gates to form a NAND gate and multiple NAND gates to form a NOR gate or any other gate. So if we are using a NOR gate, we can build any circuit just with this one gate. So this is why we call it universal gate. So both NOR and NAND are regarded as universal gates. A universal gate is gate which can implement any Boolean function without need to use any other gate type. Secondly, NAND and NOR are also used to build static storage devices. So all these SD cards, XD cards, and static hard drives, they are made up of either NOR or NAND gates, mostly NAND gates. So those devices which are called flash devices, the word flash is actually indirectly representing NAND gates. Static device means a static device which is based on all NAND gates is actually the flash device. So let's go further. Now, drawing logic circuits and finding mathematical equations and Boolean expressions. Few things before we go any further, I would like to assert on that try not to overlap input lines. If you could see over here, this line is overlapping another line over here. So try to avoid it, rather use a bridge. A bridge is a little bump in a line which shows that these two lines are different. Anyone can see that if it is crossing, it means it might be touched or it might be actually a junction where the line and where the current is being distributed over other line as well. So we have to have a little bump which shows that these two lines are different, and that bump is called a bridge. So we have to bridge it. Secondly, we cannot use the names inside the circle. So I have made these examples just to be clear that we have to form the logic circuit which is not having any lines crossing. And also I would say that we should avoid making diagonal lines. So lines, if the lines are made vertical and horizontal, the circuit uh, is actually uh, is neat, and it can, chances of understanding circuits are greater. So logic gates take binary inputs and produce the binary outputs. Several logic gates combine together to form the logic circuit. As you can see over here, we have got OR gate, AND gate, NOT gate, and OR gate. They are forming a circuit. So this is a circuit, though it is not a correct one. We will be properly making it in a short while. Okay, so let us start. So if you could see, this is, first you will have to actually keep all the gates in your mind. OR gate, AND gate, NOT gate, NOR gate, NAND gate, and exclusive OR gate. So you have to remember all those so that you could prepare these circuits properly and easily. So let us see that how we can easily make these circuits. So first of all, we have got OR gate. So let's make OR gate. Here we go. This is OR gate, and then we have got AND gate. So we have this one input going inside OR gate and one input going inside AND gate. All right, let us have a word about variables. These variables A, B, or X are representing the input, and they will always be carrying just 0 or 1. Just 0 or 1. Because this is logic gates, and logic would only be having either a 0 or 1. So then we have A going in AND, and then we have B. So remember, I told you about bridge this way. So this area is actually bridging. This bridge is telling that these two lines going from B and coming from A are actually different. And then afterwards, we use NOT gate, as we have got NOT gate over here. And then we have got one OR gate. So the output from AND gate goes to OR gate, and output from NOT gate also goes to OR gate. And the output is called X. X is just another variable. So X will be having its value, final value, which would be regarded as the outcome of this particular circuit. So as you can see, I have used vertical and horizontal lines, and I have not actually crossed the lines, rather I have used a bridge. This is absolutely necessary. Now, let's create an equation, a mathematical equation. So if you could see, this is OR gate. This is now whatever that I'm going to do over here in red is actually just the rough work. You don't have to do that. You would have to write the equation directly after having a watch over this circuit. So this is actually OR gate. So this would become A plus B. Remember, except NOT gate, whenever you get out of one OR gate, you have to put it in the brackets. This is absolutely necessary, because in any equation at O level or AS level, it is not expected that we have more than two inputs in any of the gate. So in order to maintain that two input scenario, we have to make good use of the brackets. So I'm telling it again, whenever you get out of a gate, put the output inside the bracket. That will make it sure that the output of the bracket will become one input for the next gate. So this would be, this is AND gate, so this would be A and B. So now this A plus B will go through this NOT gate, and as I said that after NOT gate you don't have to actually put a new set of bracket. All you have to do is to just show NOT. So this will be the output of OR gate that goes, once that goes through NOT gate, will become A plus B whole NOT. Now this A plus B whole NOT will go through this OR gate as one input, and then this AB will be another input to this OR gate. Now this OR gate, the output from this OR gate would be X is equal to A plus B whole NOT plus, this plus is actually this OR gate, AB. And as the saying goes, that after every gate you have to put one more set of brackets. So this is actually mathematical equation which is actually depicting this graphical representation of the circuit in mathematical form. So now if we convert this to its Boolean expression, this will become X is equal to 1 if brackets remain there, if not. As I said that this not over the bracket will, when expressed in logical, Boolean expression, will come first. So if not A or B, and then we have this OR A and B, you can see that this X is regarded as X is equal to 1 if not A is equal, if not A or B, or A and B. There is another way. There is another way showing this, which is X is equal to 1 if not A is equal to 1 or B is equal to 1 or A is equal to 1 and B is equal to 1. This might be another form that you come across in your examination. So they both are regarded the same. They are the same. There is no difference in it. They are the same. So let's get down to the next question. So NOT gate, AND gate, OR gate, another NOT gate, and then we have got exclusive OR gate. And we have X. So the equation would become X is equal to A naught plus AB whole naught exclusive OR AB. Let's see how. This is A naught, this is plus, so this would become A naught plus. This is AB. As I said that other than NOT gate, you would have to actually put everything inside bracket as soon as the input goes through a gate. So this input would go straight as well as here. This would be AB. Now you can see this is A naught plus AB. Now when this goes through this NOT gate, this would become A naught plus AB whole naught. There we have A naught plus AB whole naught, and then that when passes through exclusive OR, now you can see that this AB is being used over here as well as it is going directly into exclusive OR. So this is being used twice. So there is another piece of advice that whenever you see two same inputs, it means that you have to draw it once and use more than once, as many times it appears. Now, if we go in the form of Boolean expression, this will become X is equal to 1 if not inside the bracket. We again have to write A naught or A and B exclusive, or A and hold on. A and B. So this is another form. X is equal to 1 if not inside the bracket not A or A and B exclusive for A and B. This is another form. Now, you can always pause this video. YouTube can always wait for you. So I'm going to show you a few more examples. Pause the video over here and try to work this example out. Try to make a circuit and then mathematical equation and then logic Boolean expression out of it. Then we have got another one. You can work it out as well, and then let me work out one more, a little complicated one. So let's see how do we work it out. So A naught And then we have got AND gate, another AND gate. So no diagonal line. And then we have got exclusive OR. Here we go. And then we have got one OR. And then another OR. Now you can see this is the proper form of this circuit. And then we have got A naught, A naught B over here, B and C over here, and this would be A naught B exclusive OR B and C, and the bracket which is representing exclusive OR. And then we have A naught B exclusive OR B and C plus C, and then the bracket which is actually for this OR belongs to this gate, this exclusive OR belongs in here, and this bracket is over this OR gate. And then finally plus this last OR gate, and it is being ORed with A naught. So A naught. And the whole equation is assigned to X. Now, in Boolean expression form, this will be X is equal to 1 if one bracket, two bracket, three bracket, four bracket, not A, and B, exclusive OR bracket B and C, and then OR C or not A. This is the form. So I understand that it is not that easy to grasp at once, but you would have to do good practice in order to control it, to learn it, and to remember this. So this was our one thing that I wanted you to learn, and this was actually the first stage of steps required to cover the topic, knowing gates and drawing circuits and finding mathematical equations and Boolean expressions out of logic circuits. Okay, now we will go further and we will learn how to do vice versa. Means what if we are given the logical equations, and we are asked to convert these to the logic circuits or make Boolean expressions out of it. I'm not going to make Boolean expressions out of it, rather I will be drawing circuits directly from it. Before we go any further, the most important thing that you have to remember that it is a general delusion that A naught, B naught is equal to AB whole naught. No. A naught, B naught is not equal to AB whole naught, or AB whole naught is not equal to A naught, B naught. So do not think that way. This is absolutely necessary to remember. Now, making circuits out of equations and expressions. So first equation, we have got A plus B multiplies C. So we will work it out the way we work out mathematical algebraic expressions. So all the precedence rules will be followed. If it is bracket, we will be solving innermost bracket first, and if it is AND gate, because it is being represented using multiplication, so this will be worked out first. So let's start it. So first of all, we have to solve A plus B. As we know that this plus is actually OR gate, so this is A plus B. And then we have got the output of A plus B being ended with C. So and the output is called X. Second equation is AB naught. So AB naught, this is AND gate. A and then B naught. AB naught plus, as I said, that if you see something which has already been done, like in this case, B naught is already done. So we will be taking another connection from B naught and we'll be putting it in OR gate. So this way, we would have one B naught serving two inputs. We have got third one. We will start solving it. First, brackets on the left. So A plus B, so this is OR gate. A plus B, and then we have got multiply C means AND gate plus C. And then as you can see that A plus B is already done over here, and there is another A plus B. So we will be taking the same output again, and that will be regarded as A plus B. So the last gate that we have to use is exclusive OR. So there we go. This is our X. Remember to pause the video and understand it. Do not just go with it, practice it. If you won't, you would have trouble. Now, here, another one, A plus B multiply, which is AND gate, C and whole naught. Now it means the output of this multiplication is being inverted. It means that it can be a NAND gate or a separate NOT gate. So I will take it as a NAND gate because this NOT is being applied to this AND gate. This makes it NAND gate. Now you can see that these two brackets are exactly the same. They are being ORed over here. So it means the output from this can be doubled and can enter an OR gate. So there might be another way doing it. That is A plus B multiply C, again A plus B multiply C, as you can see, this always brings trouble in the form of more complicated drawings. And they both are being inverted and then OR. You can judge it yourself that which one is better, short and more precise. Now, Boolean expressions, we have to actually now make a circuit and mathematical equation out of the given Boolean expression. So let's see what this Boolean expression means mathematically. So this is, if A is equal to 1 and B is equal to 1, this means that this is simple AB, or not. Not means that this not means that this not is over the whole bracket. So B and C whole not, and the whole thing is being assigned to X. Now this is A, B, this is B and C whole not being ORed, and the output is X. You can do it directly as well from Boolean expression to the circuit directly, but sometimes it's a good idea to practice everything. In exam, it would be solely up to the question. That whatever the question says, you would have to do that. You don't have to actually perform all of these steps. So in B part, you have one more expression which says X is equal to 1 if not B or C exclusive for A and B or not B. So this would be B or C whole not exclusive or A and B, again brackets, or not B. This is being assigned to X, and then you can simply create the logic circuit out of it. So let's make it B plus C whole not. This is NOR gate. B plus C whole not, and then we have got AB. Now, another thing that you need to remember, it is not always necessary that you bring in lines from one variable to another gate for another input. This is absolutely okay if you represent the same variable many times. No matter how many times you are showing that variable separately, instead of bringing in lines from the first input, it is regarded as one. So if the B is being represented twice, it is still considered as one. Another option is that instead of showing C downwards, you may make the first input C and then B. In that case, we will be able to bring this B as input over here, and over here we could have made it A. Now, they both are being exclusive OR, and then it is being ORed with B naught. We can bring in input from here, make it not, and then make it input to the final OR gate. Here we go. This is one circuit done from Boolean expression. Now, I hope that you can understand this. Remember, I would assert that you should pause this video, practice it yourself, and then go further. Okay, viewers, what we have covered up till now is logic gates, making logic circuits, understanding all gates, their backgrounds, and out of that, we made circuits, and then from those circuits, we learned how to make mathematical equations and Boolean expressions, and then from mathematical equations, we created Boolean expressions and the circuits, and from logical expressions, Boolean expressions, we created circuits and mathematical equations. So this was the part one. With part two, we will learn about truth tables, building blocks, multi-input gates, and we will see few past paper questions. So thank you.